Now that we have studied Newton's three laws, let us look at some examples on how to apply these laws, especially Newton's second law. Here is our first example. Remember, in the procedure that we described above, we have to identify several things. We have to identify the system to which apply Newton's second law, then we need to draw a free body diagram, and then we need to choose a coordinate system accordingly. In this particular problem, we have a box that can slide frictionlessly down an incline, which makes an angle theta with the horizontal direction. The job is to find the acceleration of this box sliding down this incline. Now, obviously, the first step, which is to identify the system, is a very easy, simple task. It's just the box itself. It's the only thing that's moving, and that's the object, obviously, we want to study. Now, we can then draw a free body diagram, right? That's the next step. Okay, which means I need to identify all the forces exerted on this object. And to do that, like I said before, the easiest thing to do is to classify forces according to two categories, and that is contact and non-contact. Well, the only non-contact force that this box experiences, of course, is the weight. So, and that is a downward force. So I'm going to draw a downward force. Okay, that's equal to mg, assuming the mass is m. What else? Well, then you have contact force. This box is in contact with the outside world only through this surface. And what kind of contact force do we experience on this surface? Well, first of all, there is a normal force. Right? There is a normal force. Normal means perpendicular to the to the incline. So this angle is theta, just like that angle. Okay, it's clear because these two are perpendicular, and here's vertical, here's horizontal. So obviously these two angles are the same. There is no friction between the box and incline, so therefore that's the only contact force, the normal force. Okay, so we have the only non-contact force, which is the weight, and only contact force, which is the normal force, and that's both taken care of. So we have finished the free body diagram. The next step is let us choose a coordinate system, which of course in this case is just two-dimensional coordinate system, so that we can write down Newton's second law in the x direction and in the y direction. How does one choose the coordinate system? That is the key for this particular example. Now, there are two obvious choices that comes to mind. One is, how about the horizontal and vertical? Okay, after all, you know, gravity acts only vertically, and horizontal direction, there is no gravitational force. Another choice would be to follow the direction of motion of the box, so that I draw one x coordinate like this, and the y will be perpendicular to the incline. Okay, so again, two choices: horizontal, vertical, and the second one is along the incline, perpendicular to the incline. Now, let us investigate both of them. Okay, let's see. First of all, do they lead to the same final answer for the acceleration? Of course they should. And secondly, when we compare these two ways of choosing coordinate system, is there one way that's better than the other? Well, let's see. Let's look at our first choice first, and that is horizontal and vertical. So I'm going to draw a horizontal x coordinate, okay? And I'm going to draw a vertical y coordinate. Now you can call the positive direction either upward or downward according to your wish. So let's say we choose this as the x direction, and here is the upward direction is positive y direction. Okay, now this angle is of course also theta. Right? Let's take a look. The next step according to our procedure is to write down Newton's second law in both the x and y direction. So we're going to do that. Okay, first of all, what happens in the x direction? In the x direction, which is horizontal direction, this force N has a horizontal component, and that's how much it is. Horizontal component from here to there. Okay, how much is it? Well, this is N, the hypotenuse, and the angle is theta. So obviously, sum of force in the x direction from N would be simply N times sine theta, right? N times sine theta. That is the horizontal component of N. And what about mg? Well, that's a vertical force. It's got no component in x direction, so this is all there is. as far as the horizontal component of the net force. And that should equal to mass times the acceleration in x direction, right? So there we go. That's our first equation. Newton's second law applied in the x direction. Now let's apply Newton's second law in the y direction, shall we? In the y direction, I chose the upward direction as positive, so n would have an upward component in the y direction. So the component coming from n would be n times cosine theta, and that's positive because it agrees with the positive y direction. What about weight? Well, weight is downward, and it's entirely in the y direction, so it's negative mg. Okay? And what is that equal to? Well, that should be equal to m times ay, right? M times ay. Okay, so let's write it down, may. That's it, x direction, y direction. Of course, it does not move in and out of the paper, so there's no z direction to be concerned about. Now, do we have enough equations to solve for the acceleration? Well, we're looking for the acceleration. If we can find the x and the y components of the acceleration, of course, we can find a accordingly. But there is a problem, and the problem is I have a third unknown, which is n, right? How many equations do I have? I have 2 equations, and I have 3 unknowns, ax, ay, and n. Obviously, that is not enough, this pair of equations. I have to look for something in addition to that. So, what did I miss? You know, here's what I missed. Neither of these 2 equations guarantees that the object can only slide along this incline. Okay? The fact that it can only slide on the incline puts a restriction on ax and ay. For example, if this angle is 45 degrees, for simplicity, if it's 45 degrees, then you know when it moves down by 1 inch, it also has to move forward by 1 inch, right? Which means ax and ay should be the same if the box starts from rest, let's assume, right? They have the same acceleration in x to y direction, therefore they move by the same amount over the same time. That would be ax equals ay. That would be another equation that we have to consider. Now, if the angle is not 45 degrees, then ax is not equal to ay, but anyhow, they're related. That is an example of what's called geometrical constraint. Remember? That's the next thing we have to look for, geometrical constraint. So, to guarantee the object moves along the incline, I know that ax and ay are related. So how are they related? Okay, so here's the thing. The acceleration is like this, right? The acceleration is like this, along the incline. Okay, let's decompose this angle is theta. Let's decompose this acceleration. I have this component, which is ax, and that one is ay. So how are they related? Well, if this angle is theta, then you have opposite, okay, versus adjacent, that's tangent. So tangent theta equals what? Well, ay and ax, right? So ay over ax. You know, this third equation is not as obvious as the first 2. You have to dig it out, really. Okay, but it's necessary for us to use, because without the third equation, I don't have enough equations to solve everything. So now I have equation 1, 2, and 3. I have 3 unknowns, ax, ay, and n. So I can go ahead and solve everything if I wanted to. But before we do that, let's be careful here. You know, the last equation that we just wrote is almost right, but not quite. It's actually missing something. Okay? I want to emphasize this because it's very easy to overlook it. Look, I have chosen the positive x direction this way and a positive y direction to be upward. As the object slides down the incline, this is the acceleration, right? It always has a positive x component, right? But what about the y direction? You see, in the y direction, it actually accelerates downward, and yet upward is taken as positive. So a sub y is actually negative, while a sub x is positive. So the right-hand side is, as it is actually negative, yet tangent theta is always positive. So that doesn't work. I have to add a negative sign here. Okay, this is very easy to miss. So please make sure you observe that. So you see, we have the third equation with an elusive negative sign. But once we get that, then we can go ahead and solve it. In fact, let me spare you with the algebra. In fact, you can easily do it yourself if you want to. And let me just write down the result. Okay, so a sub x, you limit it n. Okay, you just find a sub x and a sub y. What is a sub x? It is equal to g sine theta squared. I'm sorry, that is a sub y. A sub y. G sine theta squared with a negative sign. Okay, you know a sub y is negative. A sub x is equal to G sine theta cosine theta, and that is positive. Okay, once you have a sub x and a sub y, you can then go ahead and find a, the magnitude of the acceleration. What is the magnitude of the acceleration? A equals the square root of a sub x squared and a sub y squared. Okay, let's work out the algebra together. All right, so I'm going to take a sub x squared and sub y squared. Look at ay and ax. They have something in common. That is, they both have a g sine theta in them, right? G sine theta, g sine theta. You square it and you take the square root, so that cancels. So I'm going to just take that common thing out, g sine theta. Okay, what do I have left? Okay, what do I have left inside the square root? Well, what's left for the ax term, there's a cosine theta that's still left, and you have to square it, so that's cosine theta squared, right? Plus, what's left in the ay? Well, there's an extra sine theta with a negative sign, so negative sine theta. You square it. Okay, so what's inside here? You have cosine theta squared and sine theta squared. That obviously adds up to 1. You take the square root, that is still equal to 1, so we finally have this very simple answer, G sine theta. Okay, there we go. That is our answer. Is this a hard problem? Well, not quite, but this third equation, okay, the geometrical constraint, is something that is not as obvious as the first two equations. We have to find it out and make sure, don't forget this negative sign. Now, what about the other choice for the coordinate system? That is, I'm going to choose one direction, which is the x direction, to be along the incline, another one to be perpendicular to the incline. Let's see if we get the same answer, and if we do, does it give us an easier way to find that answer? Well, let's see now. Suppose I redo this problem, but this time using a different coordinate choice. Okay, so I have x coordinate like this, along the incline, and y coordinate is perpendicular to the incline. Right? Okay, let me label them accordingly. This is x, this is y. The forces are still the same, of course. mg and n. So, what is this angle? That's again theta. Now, take a look. In the x direction, which is along the incline, what do I have? Well, n has no component along the x direction because it's perpendicular to it. Mg has an x component, and that's right here. This is mg, here's 90 degrees. Okay, this is mg, and that is the opposite side of the triangle. So we have mg sine theta, don't we? We have mg sine theta. That is the sum of the force in the x direction. Okay. That's it. There's no more horizontal, a component of net force along the x direction. So that's it. What is that equal to? max. But wait a minute. What about a sub x? Well, you know, acceleration generally has two components, ax and ay. But in this case, there is no component in the y direction, right? Because it doesn't move perpendicularly to the incline. It only moves along the incline. So a sub x is just the total a. So just ma. Now, we have mg sine theta equals ma. We cancel out m, what do we get? We get a equals g sine theta. We got the answer. Just like that, in one step. We didn't even touch the y equation. We just look at the x equation, and there it is, a equals g sine theta. You compare this with the kind of effort that we put in before, you know, all this detailed calculation, we get the same answer. This is much easier. So you wonder why this method is much better than the previous one. Is there a general lesson we can learn so that we can use the same trick and same technique for similar problems? Oh yes, there is. The reason why it's simpler is because the way we choose the coordinate system, a sub x is just simply equal to a. Okay, so how do we know that? Because the object can only slide along the x direction, therefore it can only accelerate along the x direction. So here is the general thing we learned. If we know for sure that an object is moving in a certain direction, okay, it moves only in this direction, then let us choose a coordinate system so that one of its axes, say the x-axis, is along this direction. Okay, that can greatly simplify our calculation because the geometrical constraint is simplified. If it only moves in this direction, then we say, let's say this is the x direction. So what is v sub y? That's 0. What about v sub z? That's also 0. You can, so this makes things a lot easier because the geometrical constraint is being simplified. Now, incidentally, if we do apply the formula, the Newton cycle in the y direction, what do we get? Well, we already know what a is, but in the y direction there is no acceleration. You have a positive component going up like this, up the incline. That's n. So sum of the force in the y direction is n. And then there is a negative component opposing to it. That's from gravity. That's mg cosine theta. So minus mg cosine theta. And that's, of course, may, right? And we all know what ay is. That's 0. Again, that's simplified because the geometrical constraint is very easily expressible here. It's just no motion, no acceleration in the y direction. So what do we learn from here? Set n minus mg cosine theta to equal to 0, and we found what n is. N equals mg cosine theta. See? So that's a bonus. That's some additional result we get apart from the acceleration a. We also learned that the normal force exerted by the incline on the box is mg cosine theta. All right, so I wanted to use this example to illustrate the importance in choosing a coordinate system wisely. In particular, if you know for sure that object accelerates or moves in a certain direction, choose that direction as one of the axes, say the x-axis. That simplifies the matter because, again, the geometrical constraint can easily be expressed. Okay, before we close this problem, let's take a look at some special cases. We learned that a equals g sine theta. That's a general formula, which we know it's correct. But can we verify that by looking at some special cases? In other words, if we take theta to a special value so that it's so special that we already know what the answer is, does our answer g sine theta agrees with that special case? So what do you think is a special case? At what angle theta do you know the answer perfectly already without any calculation? Well, one obvious example is theta equal to 0 degrees. Okay, so it's just flat, horizontal. You put the box on a horizontal table. You don't do anything to it. Is it going to move? Is it going to accelerate? No. So what's the acceleration? 0. And yes, you see, that's true. A equals g sine theta. When theta is equal to 0, you get 0. Because sine theta is 0 at theta equal to 0. Perfect. Okay, the other possibility is theta equals 90 degrees. You see, when theta is equal to 90 degrees, it's not really an incline. It's like a wall. It's like a vertical wall, okay? So the object simply moves, accelerates downward along the wall, and that's essentially a free fall, right? Because the wall doesn't give you any friction to slow you down. It's a free fall. So what do you think A is equal to? It should be equal to G, okay? It should be equal to G. And does that work? Yes, it does, because when theta equals 90 degrees, what's sine theta? That's 1, right? So that becomes A equal to G. So you see, it makes perfect sense. Now, this is an important technique. Looking at special cases, we can judge whether our answer is right or wrong. It gives us a good indication, helps us understand the problem better. As a matter of fact, even before we start this problem, if I were to give you a multiple choice, okay, I say, here are the possibilities. You pick up a correct one. A equals G sine theta, G cosine theta, G tangent theta. Which one would you pick? Well, we know this one is right? It survives both the special case of theta equal to 0 and theta equal to 90 degrees. What about that one? Well, that one is just totally wrong, because when theta equals 0 degrees, you have a flat horizontal table. The thing accelerates mysteriously with an acceleration g, and yet you suspend the box right against the wall. It's supposed to do a free fall, and yet cosine theta is actually equal to 0 when theta equals 90 degrees. So it says that theta at net equal to 90 degrees, a equals 0, that makes no sense. So this is wrong at both ends, at theta equal to 0 and 90 degrees. Now what about g tangent theta? Oh, that one is a little more interesting. It actually works all right at theta equal to 0 degrees, right? Because tangent 0 is 0. But what about theta equal to 90 degrees? Okay, what's tangent 90 degrees? That's infinity. Okay, so it doesn't make any sense, right? So therefore, this is also wrong. So you see, by looking at these special cases, I can actually have some reasonably good idea what the answer might look like. So this is correct. Those two are impossible. In fact, if I attach a number 2 here, that would be wrong. Also, because at theta equal to 90 degrees, you will get a equal to 2g instead of 1g. That doesn't make any sense either, right? So checking this special case is very instructive.